Hello and welcome back to Calculus class, Chapter 3, as we proceed with applications of derivatives. Maximum and minimum values of functions. The blue line is a function, y equals f of x. At x1, that point is called an absolute maximum. The y value is an absolute maximum, meaning it's the highest y value you will find in the entire function. At x2, we find a local minimum. The y value at the local minimum is lower than all of its neighbors, so locally it's a minimum. At x3, we have a local maximum. You'll notice that the y value at x3 is greater than all of its neighbors, so it's a local maximum. Locally, it's a maximum. And on the end here, we have an absolute minimum at x4. The y value here is lower than all the other y values, so this is the absolute minimum y value. I'd like you to notice, before we leave this, that at a local minimum, the tangent is horizontal, so the derivative is 0. At a local maximum, the tangent is horizontal, so the derivative is 0. We will revisit that concept. Algorithm for finding an absolute extrema. Extrema means maximums and minimums. And an algorithm is kind of like a recipe, a set of things to do. So an algorithm for finding absolute extrema for y equals f of x on the interval from a to b. First, find all the points on the interval from a to b where the derivative is equal to 0. Those points are called critical points. Next, evaluate f of x at the boundary points at a and b. And then thirdly, compare the y values by making a list for all these points. The largest value is the absolute maximum for the interval, and the smallest value, smallest y value, is the absolute minimum for the interval from a to b. Example, find the maximum and minimum for the given function and graph. And it looks like a cubic, and we're going to go on the interval from -5 to 3. Solution, apply the algorithm, which means we're going to have to find the critical points. For critical points, set the derivative equal to 0. So differentiating, we get f prime of x equals 3x squared plus 6x minus 24. Set it equal to 0 and solve. We can start by factoring and continue to factor, and we have x equals 2 and x equals -4. For x equals 2, y equals f of 2, and that is -28. And for x equals -4, y equals f of -4, and that is 80. So we have critical points, 2, -28, and -4, 80. Next, evaluate the boundaries, and that will be y when x is -5 and y when x is 3. So f of -5, doing the math, f of -5 is 70, and f of 3, doing the math, f of 3 is -18. So our boundary points are -5, 70, and 3, -18. So we've got 2 boundary points, and we've got 2 critical points to consider. The boundary points, -5, 70, located there, and 3, -18, located there. And the critical points that we found, -4, 80, located there, and 2, -28, located there. Join them together into our cubic, label our graph, observe it, and we can see where the absolute max is and where the absolute min is over this truncated cubic. Therefore, negative 480 is both a local max and the absolute maximum for this interval, while 2 minus 28 is both a local minimum, that's this point down here, both a local minimum and the absolute minimum for this interval. Example, find the absolute extrema of the following. And there's a function given and an interval. Solution, set f prime equal to 0. That's easy enough. F prime of x equals top thing prime times the bottom thing minus the bottom thing primes times the top thing over the bottom thing squared. And when a fraction equals 0, all we care about is that the numerator equals 0. So set the numerator equal to 0 and solve. And we get x equals plus or minus 1. That will give us our critical points. Next, what we do is make a list. We're going to need f of minus 2 and f of 4 and f of 1 and f of minus 1. Because we're going to evaluate y at the boundaries and the critical numbers. Plus and minus 1 are critical numbers. So make this list and then evaluate the y values. That's easy to do. Take minus 2 and substitute it into the original function because that's where you'll find y values. Don't sub it into the derivative. And I got negative 8 over 5, 16 over 17, 2, and negative 2. And so there's your absolute max because that's the highest, and that's the absolute min because that's the lowest. Example, the concentration C of T in milligrams per cubic centimeter of a certain medicine in a patient's bloodstream is given by a function, where T is the number of hours after the medicine is taken, or possibly injected. Determine the maximum and minimum concentrations between the 1st and 6th hours after the medicine is taken. Solution, set C prime of T equal to 0. Okay, top thing primed times the bottom thing minus the bottom thing primed times the top thing over the bottom thing squared is equal to 0. We've got a fraction equal to 0. We just care that the numerator is equal to 0. And we'll do our common factoring thing in order to solve this. That's why we learned a common factor. We see that 0.1 comes out of both the terms. We see that t plus 3 comes out of both of the terms. So common factor them out. This is the residue left behind by these two big terms after we common factored out these two factors. Simplifying, and we have our t values. There is a critical point at t equals 3. It looks like there might be one at t equals negative 3, but time generally starts at 0 if we're going to measure concentration after medicine was taken. So time starts at 0, so we can ignore the t equals negative 3 solution. So t equals 3. There is a critical point at t equals 3, and we're interested in the concentration at 1 hour, 3 hours, and 6 hours. Plugging the numbers in, at 1 hour there was 1/160th of a milligram per milliliter. At 3 hours, after it circulated in the blood for a couple of more hours, it was more concentrated at 1/120th of a milligram per milliliter. And then after 6 hours, it had begun to decline back. It had become less concentrated. So from this data, we can conclude that the maximum concentration of medicine was reached at the 3-hour mark, 1/120th of a milligram per milliliter.